Good afternoon, everybody. Today is the lecture number 5 from the course on thermodynamics, and today I would like to talk about phase transitions. What is phase transition? Well, an example of phase transition is shown on this slide. This is an example that you may observe every day in your life. This is a transition between ice and water. So as you can see on this slide, that in principle, under certain circumstances, water and ice can coexist. In this lecture, we will call a substance which is physically and chemically homogeneous as a single phase. So the phase would be a substance which is physically and chemically homogeneous. It could be either water or ice or gas, or more general, different states of aggregation as gas, liquid, different crystalline states would be considered as different phases. Phase transition. Transition of matter from one phase to another phase is called phase transition. So in this case, if I talk about transition from state of water to state of ice, it will be an example of phase transition. And I will refer in my lecture several times to this phase transition that we observe every day in our life and we have a good intuition for. Problem number 1. So as I showed, in principle you can achieve a situation when two phases, phase of water and phase of ice, coexist. There will be border between these two phases. Imagine the border looks like this, and there will be pressure 1 and temperature 1 on one side of this border in phase 1, and there would be pressure 2 and temperature 2 on another side from this border, and we will call it phase 2. More particularly, it could be water and ice or water and vapor. And as I said, there is a border that separates these two phases in space. Obviously, if we achieve the situation of equilibrium, thermodynamic equilibrium, then we can expect that not only pressures from both sides of the border, but also temperatures from both sides of the border are mutually equal. Now, I would like to understand the behavior of this border, and I would like to understand the conditions for the equilibrium between phase 1 and phase 2. In theory, in particular, I would like to answer a question: how will the phase boundary change if we change pressure or temperature? Well, if you want to understand something in thermodynamics, we showed that you have to start with choosing right variables and choose right thermodynamic potential. The variables in our case are pressure and temperature. Then we write first law of thermodynamics. If we talk about reversible processes, heat would be equal to temperature times change of entropy. And if we talk about situations when pressure is involved, then work performed on the system would be pressure times change in volume. And it means that the first law of thermodynamics will be written in this form that we did already several times during this course, and from where you can see that internal energy, it is thermodynamic potential, but the problem of this thermodynamic potential that it has volume and entropy as variables, and we would like to have a thermodynamic potential for which it is pressure and temperature variables. If you want to derive a potential like this, let's call it G. It is possible if you define potential in this way, so you can check it yourself, then if you calculate differential of G, it would be equal to minus S dt plus V dP. The derivations are very simple. I show this on the slides. You can easily repeat it. Repeat the derivations yourself. Okay, further I will work with this thermodynamic potential. And this thermodynamic potential in literature is called Gibbs function. I would like to use Gibbs function, but with one small upgrade. I would like to operate with quantities which do not depend on mass. For this, I will introduce specific Gibbs function. It will be Gibbs function divided by the mass. And now I will use this language of Gibbs functions to describe thermodynamic equilibrium between two phases. The problem here is that I will talk about inhomogeneous situation. So there would be some thermodynamic potential assigned to phase 1, and there would be second thermodynamic potential assigned to phase 2. So then it means that if I talk about total thermodynamic potential, it would be thermodynamic potential of phase 1 plus thermodynamic potential of phase 2. And as I said already, we can rewrite this expression in terms of specific Gibbs functions, G small, where M1 and M2 are the masses of phase 1 and phase 2. Now I calculate differential of the Gibbs function, and it will be given by the differential of the sum. And as you can see from here, the expression for this differential will have 4 terms. But now I can benefit from the fact that in my problem I consider situation of thermodynamic equilibrium. Thermodynamic equilibrium means that Gibbs function J and specific Gibbs function are at minimum, and in thermodynamic equilibrium these quantities do not change. So it means that this quantity would be 0, this quantity will be 0, and this term will be 0. And what I get at the end is that G1 plus is equal to 0. Then I'm talking here about a phase transition of matter from phase 1 to phase 2, but even if there is transition, total mass is conserved. So it means that if I'm talking about changes of mass in phase 1 or in phase 2, the total mass shouldn't change, and from these two expressions I eventually arrive to a very important equality that says that if I'm talking about thermodynamic equilibrium of phase 1 and phase 2 at the phase transition, then thermodynamic equilibrium implies that specific Gibbs functions of phase 1 and phase 2 are mutually equal. This is the main statement that allows us to build up thermodynamic theory of phase transitions. In thermodynamic equilibrium, phases have equal specific Gibbs functions. Now, let's look at the behavior of these specific Gibbs functions as a function of pressure and temperature. So if you now plot J as a function of temperature and pressure, then of course if this specific Gibbs function depends on both variables, it will correspond to some surface in 3 dimensions, and one surface would be assigned to phase 1, and it means it will describe behavior of the specific Gibbs function G1, and there would be second surface that will describe behavior of the specific Gibbs function G2. Here these two surfaces will intersect, and here we will have equality of the specific Gibbs functions, and it means that here at this line we will have equilibrium of phase 1 and phase 2. Very important thing to notice here is that in accordance with the general principle of thermodynamic potentials, if I'm talking about thermodynamic equilibrium, the total thermodynamic potential of the system should be at minimum. So it means that if we are talking about a mixture of these two phases, and the matter in one phase will have lower specific Gibbs function than the matter in another phase, the requirement for the minimization of the total thermodynamic potential will force the medium to come from state 1 to state 2. If this coefficient is smaller than this one, then in order to minimize this quantity, you will have to transfer more mass into the second phase. And this would be the situation on this side of the diagram. But then if you change temperature or change pressure, the conditions are also changing, and here on the other side of this line it would be already phase 1, which has smaller specific Gibbs function. And if this is a phase 1 which has smaller specific Gibbs function, then for the medium it is energetically more profitable to transfer more and more mass into this phase, and in this case minimize total Gibbs function, total thermodynamic potential. So it means that medium, the thermodynamics will force the medium to have a transition from state 2 to state 1. And here these two phases, as I said already, will be in thermodynamic equilibrium. What people often do, they project this line onto the surface P and T, then they have something like, so then a dependence like this, and then they can say that on one side from this line it would be phase 2, which is in thermodynamic equilibrium. On the other side of this line it would be state phase 1 that corresponds to the thermodynamic equilibrium. And along this line these two phases can coexist because they are equally because they have equal specific Gibbs functions. A dependence like this is called phase diagram. Now we would like to understand how to describe phase transition using mathematics, and in particular how to describe phase transition from the state of water to state of ice. In order to develop theory of phase transition, Ehrenfest proposed a very nice and very intuitive classification of phase transitions. his idea was the following. Well, there is a phase 1 and specific Gibbs function is described by some surface. There is a phase 2 with specific Gibbs function which is described by another surface. Here, at the phase transition, they have equal specific Gibbs functions. But if at the phase transitions they have equal specific functions but still they belong to different surfaces, then somewhere, even if you look at the transition, somewhere these functions should be different. And it could be either first derivative with respect to temperature, or first derivative with respect to pressure, or second derivative with respect to temperature, or second derivative with respect to pressure, and so on and so forth. So more particularly, Ehrenfest proposed to look at specific Gibbs functions of phase 1 and phase 2, although at the phase transition they are mutually equal, but since these specific Gibbs functions are described by different surfaces, then there is a chance that if you look at the first derivative of specific Gibbs function with respect to temperature while keeping pressure fixed, then this derivative will experience discontinuity upon transition from state 1 to state 2. Or if you look at the first derivative with respect to pressure while keeping temperature fixed, it can also experience discontinuity. Or it could be different situation when first derivatives are still mutually equal, but it is second derivative that experiences discontinuity. And the proposal of Ehrenfest was to look at the order of the derivative, lowest order of the derivative, where we observe the discontinuity for the first time. And if it is already the first derivative where specific Gibbs function experience and jump, we will call it first order phase transition. If first derivative is still a function without a jump, but then it is the second derivative which experiences the discontinuity at the phase transition, we will call it second order phase transition. If first and second derivative do not show discontinuity at the first transition, but it is third derivative with a discontinuity, we will call it third order phase transition. So the rule is the order of a transition is defined as the order of the lowest differential of the Gibbs function or other thermodynamic potential, which shows discontinuity at the phase transition. Let's consider the case of first order phase transition. Imagine that this is a phase diagram, pressure, temperature, line that separates two phases on phase diagram. This is point A, this is point B. So along this line, these two phases are in mutual equilibrium. Then I will operate with the two functions, specific Gibbs function 1, which is equal to entropy of the first phase divided by the volume of the first phase divided by the mass of first phase plus volume of the first phase divided by the mass of first phase times differential of pressure. Or for the second phase, we write something very similar. And in future, we will also call as small as a specific entropy, total entropy divided by mass, and nu is total volume divided by mass. So basically it's an inverse density, inverse mass density. So I'll operate with these two functions. And here I first look at this function and I notice that this is exact differential. It is a function of state, and this because this is a function of state. I can write this differential as a sum of two terms. And the same will be done for the second phase. At the phase boundary here, as I said, specific Gibbs functions of these two phases are mutually equal. But also, if you stay on this phase boundary while changing pressure and temperature, you succeed to go along this phase boundary without going either in one or another phase, but you succeed to keep the equilibrium with these two phases. So it means that also the changes of these two specific Gibbs functions would be equal. And if you use all these three expressions, you can write that we can write that we have a quality like this. And here it is a moment to look carefully at this derivative. If you look carefully at this derivative, you will see that in general this derivative is equal to specific entropy. And in general, this derivative will be equal to volume of unit mass. As defined previously. So then if you look at this expression, what you obtain here specific entropy of first phase change of temperature plus specific volume of the first phase pressure, then the same would be valid also for the second phase. And bringing this expression in a more compact form, we obtain an expression like this. It can also be written as total entropy change and total volume change. So assuming that this is the first order phase transition, we found an expression for the derivative of pressure with respect to temperature for this line, for the line that separates two phases on the phase diagram. Well, if you look carefully and if you look at the definition of S, it will be also defined, the change of entropy will be also defined as a heat supply to the system divided by temperature. So as we know, phase transitions like melting of water and melting of ice, transition between ice and water occurs at constant temperature. So in principle, the very same expression can be written in this form, where L would be the heat which is needed to promote the phase transition. Well, let's look more carefully into this expression, which is called Clausius-Clapeyron equation. So this is an expression that describes first order phase transition. An example, phase transition between state of water and state of ice. Is it first order phase transition or not? Let's look at this derivative. This derivative is not infinitely large and it's not zero if we have delta S not equal to 0 and delta V is not equal to 0. If you talk about transition between water and ice, the volume changes. We know that. If you know about phase transition between water and ice, also entropy changes. And we also know this because entropy can be expressed in terms of ratio of heat supplied to the system divided by temperature. And we know that in order to melt ice, we need to supply heat to the ice. So in principle, already from this expression, we can see that first order phase transition can in principle describe melting of ice. Or you can look at this differently. How do we know that melting of ice is the first order phase transition? Well, we know this more or less by definition, because first order phase transition means that upon transition from state 1 to state 2, derivative of the specific Gibbs function experience a jump. And what is derivative of the specific Gibbs function with respect to temperature means? It means entropy of unit mass in phase 1 is not equal to entropy of unit mass in phase 2. So it means that if we assume that this is first order phase transition, and if this is first order phase transition due to discontinuity of specific Gibbs function with respect to temperature, we practically by definition already assumed that entropy will experience a jump at the phase transition. If entropy experiences a jump, it means that we need to supply heat to promote the phase transition. Similarly, you can look at another derivative, the one with respect to pressure. And if this derivative experiences a jump, it means that specific volume of unit mass for one phase is not equal to volume of unit mass for another phase. So you can say mass density for one phase is not equal to the mass density of another phase. So it means that at the phase transition, volume will change. It's again something that we already predefine when we say that we're talking about first order phase transition. That's why observing phase transition of that corresponds to the situation of melting of ice, transition between state of ice to state of water, we can actually talk about first order phase transition in thermodynamics. Let me summarize main features of first order phase transitions. So if you observe something experimentally and you would like to understand if it is the first order phase transition or not. As we discussed, feature number 1, if we observe abrupt change of volume at the phase transition, it must be assigned to first order phase transition. If we observe abrupt change of entropy at the phase transition, or differently, if in order to promote phase transition we have to supply latent heat. So you supply heat and temperature doesn't change. So that's why we call it latent heat in heat theory, Warmte layer. If this is the case, then we are talking about jump in entropy at the phase transition. It is again signature of first order phase transition. For similar reason, since you supply heat to promote first order phase transition and the temperature doesn't change, the heat capacity, as we define this in our course, will go to infinity. And very important thing, coexistence of phases and hysteresis. Okay, hysteresis. What does it mean, hysteresis? Well, if you consider a phase transition between state of water, for instance, liquid state of water, and vapor state of gas, and my statement is that if you increase temperature very slowly, and if you do experiment carefully, then the phase transition between water state and gas state will happen at one temperature. But if you now decrease temperature, you will again promote the phase transition, but back from gas phase to liquid phase. And I claim that if you do this experiment properly, the phase transition should occur at lower temperature. And the shape like this, if you plot, for instance, mass density as a function of temperature, shape like shown on this slide, is called hysteresis. How do I understand this hysteresis? So how can we explain it physically? Well, we have two surfaces that correspond to specific Gibbs functions. And if we are looking at the total Gibbs function, the nature tries to minimize this total Gibbs function. So then if we are in the state where G1 is smaller than G2, then the nature will try to transfer more and more mass into phase 1 in order to obtain minimum possible value for total Gibbs function. So now let's look at the mechanical analogy. Imagine that I have a situation when temperature of my experiment is much smaller than the temperature of phase transition. And then means that the second phase even doesn't exist. The second surface of the specific Gibbs function even doesn't exist at this temperature. And if you're talking about a mechanical analogy, it would be profile of potential energy, and it would be ball just at the minimum. The ball tries to minimize its potential energy. Then you increase temperature, you come closer to phase transition temperature, this critical temperature, and then the second surface appears, and the second surface will correspond to a state with a minimum of potential energy, where the second surface would be at higher values of specific Gibbs functions. That's why in mechanical analogy it will correspond to minimum with larger potential energy, and for ball it would be still more energetically profitable to stay in this state. Then at the temperature phase transition, these two states have equal specific Gibbs functions, and it means that for ball it doesn't matter in which minimum to exist. Either here or here the potential energy would be the same. Then you increase temperature further, and then this minimum already becomes energetically more profitable, the minimum that corresponds to the second phase. And eventually this first state will disappear. Well, let's still write it like this. It is about, this first state is about to disappear, and system, so the ball will overcome this very small potential barrier that separates these two phases and will drop to the second phase. So this is phase 1, this is phase 1, this is phase 2, this is phase 1, this is phase 2, this is phase 1, this is phase 2, and this is phase 1, this is phase 2. So here, at this temperature, let's call it T prime, we have phase transition from phase 1 to phase 2. And now, the ball is in this state. I decrease temperature. Ball is still in this state. I decrease temperature. Ball will be still in this state 2. I decrease temperature further, then potential barrier is already small. So imagine that it's small enough that the ball can overcome this barrier, and then it will drop here. And eventually, here I have transition from state 2 to state 1. And previously, I had transition from state 1 to state 2 at this temperature. So what we had phase transition from state 1 to state 2 at temperature T prime, and the phase transition from state 2 to state 1 in temperature double prime. Different temperatures, so exactly as I showed at the figure. Well, you may ask yourself, well, why don't we observe this effect experimentally? Well, as I said, you should do experiment properly. There is a very nice example of overheated water that you can see in this movie. We heated the glass of water above the boiling point in a microwave oven. Above 100 Celsius degrees, the liquid phase of water has a larger specific Gibbs function than the gas phase. If there are no bubbles in the liquid, the boiling doesn't start. But once we create the very first bubble, by shaking the liquid, the boiling starts explosively. By creating the bubble, we create a real physical boundary between the gas phase and the liquid phase. The boundary moves and the bubble expands explosively, aiming to transfer more mass into the gas phase and thus to minimize the total Gibbs function. And as we discussed previously, melting of ice is another example of first-order phase transition. It's another example where we should see coexistence of ice and water and temperature hysteresis. And there is also a phenomenon of supercooled water that you can see in this film. We cooled a bottle of water in the fridge below the melting point, below 0 Celsius degrees. At this low temperature, the liquid phase of water has a larger specific Gibbs function than the solid phase. If there are no crystals of ice in the liquid, the crystallization doesn't start. But if we shake the bottle, we create the very first crystals. In this way, we create a real physical boundary between the solid phase and the liquid phase. The boundary moves and the crystal expands, aiming to transfer more mass into the solid phase and thus to minimize the total Gibbs function. Next interesting question is coexistence of several phases. So here on this slide, I plot two cases. The one corresponds to water and another one CO2 gas. So as you can see here, there is a phase diagram for three phases: gas phase, liquid phase, and solid phase. There is one nice point at this phase diagram at which all three phases coexist: gas phase, liquid phase, and solid phase. And this point is called triple point. So this point corresponds to a point at which all three surfaces corresponding to specific Gibbs functions of three phases mutually cross. So let's look at the Clapeyron equation and look at another very nice feature of this phase diagram, and in particular to the line that separates solid phase and liquid phase for the case of water. Obviously, in contrast to the phase diagram for CO2 gas, we can notice negative derivative for this line, negative derivative of pressure with respect to temperature. So it means that if you increase temperature and you promote the transition from solid phase to liquid phase, you will have to provide the heat, obviously, and the heat is positive, but it will also mean that change of volume is negative. So it means that upon transition from solid phase to liquid phase, water decreases in volume. So another way around, if you freeze water, it will increase in volume. And this is a unique feature of water, and you can search on internet there are also claims that due to this feature of water, we still have life at the Earth. So water expands upon freezing. And another very unique feature of water is that if you increase pressure at fixed temperature, you can find water in all three phases: gas phase, liquid phase, and solid phase. That corresponds to red line on this phase diagram. So in particular, you can see here that water can melt under pressure. So this point corresponds to triple point. And it's very interesting to look at other compounds like helium. And helium has not 3 but 4 possible phases. It has gas phase, as we all know. Helium can be found in 2 liquid phases. One is called liquid, another one is superliquid. And the 4th phase is solid phase. You can see that for helium we observe not 1 but 2 triple points. The third red dot on this diagram corresponds to so-called critical point, but let's talk about this critical point at the questions and answers hour if you are interested. And here I would like to emphasize that helium becomes liquid at very low temperatures. And this played a very important role in physics of 20th century. In particular, people wanted to reach these very low temperatures because at the end of 19th century there was a very hot discussion about the behavior of electrical resistance upon temperature decrease. There was a group of scientists who claimed that if you decrease temperature and measure resistance, the resistance should go to infinity, because resistance that describes the electrical current. Current is a motion, and if you decrease temperature, nothing moves. So it means if you approach 0 Kelvin, motion stops, current will stop, and the resistance will go to infinity. There was another group of people who claimed, no, resistance, so it's about charged particles, charged particle moves, and resistance comes due to the fact that these charged particles get scattered. If we approach 0 temperature, scattering would be less and less efficient, and eventually at very low temperatures there will be no reason for particles to scatter, and it means that the resistance will go to 0. And there was a third group of people who were just in between, who said, well, there are no pure materials in this world, and because all materials have defects, the situation would be somewhere in between. These two extreme theories can be also described in terms of energy diagrams for electrons. So if you're familiar with the energy of diagram of electrons in semiconductors, you can imagine these two situations. If not, let's skip it. And it was Kimel and Onnes in the beginning of 20th century who wanted to figure out which of these two theories, extreme theories, is correct. Whether the resistance goes up when you approach 0 temperature or it goes down. That's why he synthesized liquid helium. And the idea was to get liquid helium, to put material into helium and measure resistance. And it was a very lucky choice of Kimel and Onnes to take mercury. And he did it in order to avoid discussion with scientists who claimed that most likely what you will observe would be the result of impurities, and he took the most pure material possible at that time. He took mercury. And it was a beginning of great discovery, probably one of the most important discoveries in physics of 20th century. What he observed when he decreased temperature at temperature 4.2 Kelvin, the resistance of mercury suddenly dropped and became 0. Kwik nagenoeg nul, what he wrote in his lab book. So actually it was the discovery of superconductivity. There was no resistance for electrical current. So if you make a wire of a superconducting material and you let current flow through this wire, as long as the material would be superconducting, the current will flow, and as we all know from electromagnetism, it will generate magnetic field. It will be magnet. Superconductors are counterintuitive. So if you get a material in superconducting state and if you drop magnet on it, magnet will start levitating. Why it happens? Because superconductors, as I said, they repel magnetic fields. So what happens when magnet approaches superconductor, it generates electric current. As we all know from the law of electromagnetic induction, the direction of the current is such that it generates magnetic field exactly in the opposite direction with respect to the magnetic field created by the magnet. And in this way, since superconductor, the currents on the superconductor do not experience any resistance, within the superconductor, magnetic field would be compensated. It would be zero. So the lines of magnetic field will avoid superconductor. And if you measure total magnetic moments of a material which at high temperature in simple metallic state and at low temperature in a superconducting state, in both cases we will talk about so-called diamagnetic material. So it means that it will try to compensate magnetic field that acts on it. So it will try to decrease magnetic field that acts on it. But in case of superconductor, it will do it much more efficiently than in the case of metal. And then if you calculate the difference, magnetization of normal metal minus magnetization of superconductor, you will get something larger than zero. And if you haven't heard anything about superconductors, so now it is a chance to learn about superconductors using thermodynamics. In particular, people studied superconductors as a function of temperature and as a function of magnetic field. And as I said already, if you decrease temperature, normal metallic state of a material can become superconducting state. But now, if the material in the superconducting state, even at low temperatures, but if you increase magnetic field, you can again destroy superconducting state, and get material into normal metallic state again. So if you measure critical magnetic field at which superconductivity is destroyed, as a function of temperature, you will get a line like this, like shown on this slide, and this line corresponds to phase diagram. But if previously we were talking about phase diagram in the coordinate system pressure and temperature, now we're talking about phase diagram in the coordinate system magnetic field and temperature. And as I announced, let's study superconductivity using these tricks of thermodynamics. And for this, we choose right set of variables. It would be temperature, magnetic field, and pressure. We choose right thermodynamic potential. We formulate specific Gibbs function. For this case, at the boundary, the specific Gibbs functions of superconducting state and metallic state should be mutually equal. Then we repeat the very same trick as we did during the derivation of Clausius-Clapeyron equation. The change of the first specific Gibbs function, the change of the second specific Gibbs function, the fact that at the boundary they are mutually equal and the changes of these two specific Gibbs functions are mutually equal. Then we write this down and obtain the very similar expression as we did when we discussed phase diagram pressure and temperature. Now we have an expression for the phase diagram magnetic field and temperature. And as you can see, that since entropy always increases when you increase temperature, entropy should increase upon transition from superconducting state to normal state. And since difference in magnetization between normal state and superconducting state is also positive, as I showed before, it will immediately give you that the derivative of magnetic field with respect to temperature should be also negative, and it is exactly what we observe experimentally. So this is something in agreement with the experiment. So as you can see, at least in the case of first order phase transitions, classification of Ehrenfest is rather powerful. But what about second order phase transitions? If you talk about second order phase transitions, there is a problem, at least in the case of classification of Ehrenfest. Let's look at this problem. So we have two specific Gibbs functions. Their first derivatives are mutually equal. But if you look at the order where derivative experiences a discontinuity, it will be the second order. So we draw how specific Gibbs function at fixed pressure depends on temperature. It would be, for instance, line that corresponds to the first specific Gibbs function. It would be the line that corresponds to the second specific Gibbs function, and the derivatives and the values are equal at the critical temperature, temperature of phase transition. And if you look at this diagram, you don't understand why the phase transition should happen at all. Whatever temperature is, specific Gibbs function that corresponds to the second phase is always smaller than specific Gibbs function that corresponds to the first phase, and then there is no reason, thermodynamic reason, for the phase transition from the second phase to the first phase, because all the material in the second phase, total Gibbs function would be minimized. So in the classification of Ehrenfest, there is a problem. How to resolve the problem? Well, the solution to the problem was proposed by Landau and Ginzburg, who suggested to classify phase transitions as first order phase transitions or abrupt phase transitions and continuous phase transitions. What do they mean by this? That if you look at the specific Gibbs function of or any other thermodynamic potential that changes as a function of temperature, if we have a discontinuity in the first derivative of the specific Gibbs function, we will call it first order phase transition. If the transition is such that the first derivative doesn't change, so it means the function changes continuously, we will call it continuous phase transition. And it happens such that later continuous phase transitions started to be called second order phase transitions. And in this case, it means it is not first order. Let's look at the modern view of first order phase transitions and second order phase transitions or continuous phase transitions. So that if you talk about first derivative of thermodynamic potential, as we showed, first derivative of thermodynamic potential can be volume, entropy, but also magnetization, electric polarization, depends which thermodynamic potential you use. And if we have a situation of first order phase transition, first derivative should experience a jump, and it means that volume, entropy, magnetization, polarization, or other observable will experience a jump at the phase transition if you study this experimentally. If you measure second order phase transitions, these quantities change continuously. No discontinuity at the phase transition should be observed. So if you look at the first order phase transition and the first derivative of the thermodynamic potential like volume, entropy, magnetization, polarization, at the first order phase transition, it will experience a jump. And if you look at the very same observable, but at the second order phase transition or continuous phase transition, it will change continuously. Eventually brings me to the conclusions. I hope I was able to show you that thermodynamics allows to build a theory of phase transitions. Ehrenfest classification of phase transition was introduced, but is shown to be incomplete, so at least we don't have a good explanation for second order phase transition in the theory of Ehrenfest. But modern view on the classification of phase transitions was described, in which we distinguish phase transition between two groups. And the first group is the first order phase transition is in full agreement with the classification of Ehrenfest, and the second group it corresponds to continuous phase transitions in which observable is changed continuously. Thank you very much.